Number 40 says write the equation of the following polynomial in factored form. Note you will use a leading coefficient of -1 or 1. Okay, so that means all we really need to do is look at the x-intercepts, which correspond to the factors, and the end behavior, which corresponds to whether the leading coefficient is positive or negative. So the x-intercepts look like -2, +2, and +5. So those are the real zeros. X equals -2, x equals +2, and x equals +5. So the factors that would correspond to those zeros would be x plus 2, because if you set that equal to 0, you get x equals -2. X minus 2, setting that equal to 0 would give you x equals 2. And x minus 5. And when you have 3 linear factors, that gives you a third degree polynomial. So the end behavior would be up on the right and down on the left, which is exactly what this has. So the leading coefficient is just +1, and that's the answer. Number 41, write the equation of the following polynomial in factored form. Again, a leading coefficient of -1 and 1. All right, so this one has x-intercepts at -3, 0, and 6. But this one right here is special. This one, it just touches down. It's tangent to the x-axis. That happens when that is a 0 of multiplicity 2 or 4, an even multiplicity, meaning that the factor that corresponds with that x-intercept is either squared or to the 4th power, and we can just have it squared since it doesn't specify. So 41, we have, again, the zeros or x-intercepts of x equal -3, x equals 0, and x equals 6. And this one is sometimes called a double root because that factor, the factor that corresponds to it, appears squared twice. So we're going to have an x plus 3, an x minus 0 squared, and an x minus 6. Here, this is going to give you a 4th degree. In fact, this x minus 0 we can just write as x squared. So I'll put that out in front, x squared, and then x plus 3, and then x minus 6. And those factors, hopefully you can see, would give you a 4th degree polynomial. 4th degree polynomial goes up on both ends or down on both ends. This one goes down on both ends, which happens when you have a negative leading coefficient. So just putting a -1 coefficient here, just a negative, does the job for that one. And you can always try typing these into your calculator and check them, graph them on your calculator and check that they do look like the graph they're supposed to. Number 42 says determine the coordinates, that should be 2 S's, 2 coordinates of removable discontinuity, the whole for the function f of x equals x squared minus 81 over x minus 9. All right, so this function has a undefined spot when its denominator is 0. But instead of being a vertical asymptote like it usually is, it turns out to be a hole, and that's because this numerator factors difference of 2 squares, and that x minus 9 in the denominator actually cancels. So except for at that value, this function is actually equal to the linear function x plus 9. In fact, if you graph it, you'll see it looks like the line with y-intercept 9, slope 1. But it does have a hole at the spot where it's undefined, which is when this denominator is 0, which is x equal +9. So there's what's called a removable discontinuity. An asymptote is non-removable. You'll learn more about this if you go to calculus. If you take calculus, you'll learn about more about continuity and limits. So this one has a hole there, and to get the other coordinate, the y-coordinate, you plug the value of 9 into this simplified version. Plug 9 in for x here. 9 plus 9 gives you 18. So there's a hole at the point 9, 18. Number 43 says determine the equation of the slant asymptote for the function f of x equals x squared minus 5x minus 2 all over x plus 1. All right, a slant asymptote is often called an oblique asymptote, and it only happens when the degree of the numerator is one more than the degree of the denominator, so it's a linear quotient, so that tells you the graph goes off linearly. It doesn't have a horizontal asymptote. You might remember that it has a vertical asymptote when the denominator is 0 here, because that one doesn't cancel out, so it's not a hole. To break in the domain, just like up here, x equals 9 was a break in the domain, but here it was a hole because it canceled out. Here, this numerator doesn't even factor, so that doesn't cancel. So it's just a vertical asymptote. The oblique asymptote or slant asymptote is gotten by actually dividing with synthetic division. So you go make your division symbol. We're dividing by x plus 1, so -1. X equals -1 is the spot we're looking at. The coefficients are 1, -5, and -2 for that quadratic. 1, -5, -2. So those go inside the division symbol. Leave a space, draw a line, bring down the 1, multiply, you get -1, add, you get -6, multiply, +6, add, you get 4. All right, that's the remainder. We don't care about that. What we care about is this quotient, which is 1x minus 6. Y equals x minus 6 is what that graph approaches. In fact, it's probably worthwhile to look at this one on the calculator. If you graph, let's see, let me clear this out. This one, remember for rational equations, to type them in, you've got to put the numerator and denominator in parentheses. So x squared minus 5x minus 2 goes in parentheses, divided by the quantity x plus 1. And let me graph that oblique asymptote that we found too. Y equals x minus 6 as y2. And you'll see that it gets closer and closer to that. Let's see if a standard window shows us what's going on. So there's part of it, there's the line. So we can only see half of it. We see the part that's to the right of the vertical asymptote. Probably have to extend your window down and or to the left. Let's see if we go down to -20 on y. Let's see what that shows. Yeah, there's the other piece. There's a vertical asymptote here at x equal -1, and then sure enough that slant asymptote is what it approaches. And that's because, you know, when you divide, you get a quotient, in this case x minus 6, plus a remainder, which is 4, and so you could write this as that quotient plus the remainder over the divisor. And when x gets really large, this fraction gets closer and closer to 0. So that shows you that it gets closer and closer to this line. So that oblique asymptote is kind of like end behavior. Shows you what's happening on the ends as x gets really large in the positive direction or in the negative direction.